Hey everyone, and welcome to the Rust Crash course, part of the blockchain development series. My name is Ben-Hur Mwamba, and over the next 45 minutes or so, I'm going to take you from absolutely zero knowledge of Rust to writing, running, and testing real Rust code. Now, you might be wondering, why Rust? Why not just use Python or JavaScript or Go? That is a great question, and we're going to answer it thoroughly in this session. But the short version is this. If you want to write smart contracts on Stellar, or really any blockchain platform that values performance and safety, Rust is the language you need to know. It's not optional, it's foundational. This course is focused on three things: safety, performance, and ownership. Those three words are going to come up over and over again in this session, and by the end of this video, you understand exactly what they mean and why they matter. This is marked as modern and technical, meaning we're not going to dumb things down. We're going to treat you like a dev that you are, or the developer that you're becoming. So let's get into it. This is module 1 of this course, and it's titled Rust Foundation and Toolchain. In this module, we're going to cover three big areas. First, memory safety guarantees without garbage collection. What does that mean? We'll break it down. Second, the cargo ecosystem, the build tool, the package manager, the essential commands you'll use every single day. And third, variables, mutability, shadowing, and expression, the core building blocks of writing actual code, actual Rust code. And by the end of this module, you'll have a solid mental model of what makes Rust special, and you'll be able to create, build, and test your own Rust project from scratch. All right, let's start with the most important question. Why Rust? Why does it exist at the first place? To answer that, let's talk about two worlds that exist before Rust. On one side, you had languages like C and C++. These languages are incredibly fast. They give you direct control over memory, no overhead, maximum performance. But the trade-off is that you are responsible for managing memory. You allocate it and you free it. And if you make a mistake, if you access memory you've already freed, or if you write past the end of a buffer, you get crashes, security vulnerabilities, and bugs that are notoriously hard to track down. On the other hand, you had languages like Java, Go, Python, JavaScript. This added a garbage collector. So this is an automatic system that tracks which memory is no longer being used and frees it for you. It's much safer, but now you've added runtime overhead. The garbage collector runs in the background, and occasionally it has to pause your whole program to do its work. In most applications, you don't notice, but in high performance systems like blockchain, those pauses matter. So the question Rust asked was, can we have both? Can we have C-level performance and memory safety without garbage collector? And the answer is yes. And here's how Rust delivers on this promise. Memory safety. Rust eliminates entire classes of bugs at compile time, so not at runtime, at compile time. Things like null pointer exceptions, use after free errors, and data races simply cannot happen in safe Rust code. The compiler catches them before your program ever runs. And second, zero cost abstractions. Rust gives you high level syntax, things that look clean and expressive, but compiles them down to the same machine code you'd write in C. The phrase used in Rust community is, what you don't use, you don't pay for. You get comparable speed to C and C++. And third, reliability. There's a famous saying in Rust community, if it compiles, it usually works. That sounds almost too good to be true, but it reflects the reality that Rust's type system is so strict that a huge range of logical errors are caught at compile time. Look at the code example on this slide. We create a string called s1. Then we assign s2 equal s1. At that point in Rust, s1 is no longer valid. Ownership has moved to s2. If we try to print s1, we get a compile error. The comment says error, but printing s2 works fine. It's safe. No unexpected runtime crashes. That concept of ownership is the heart of how Rust achieves all this. We'll go deep on it in a later module, but keep it in the back of your mind for now. Let's go one level deeper. We just said Rust has no garbage collector. So how does it manage memory? Through its ownership system. Memory in Rust is managed through a set of rules that are checked at compile time. There's no garbage collector running in the background. There's no runtime agent tracking your memory usage. Instead, the Rust compiler itself enforces rules about who owns each piece of memory, when it can be accessed, and when it gets freed. If you break the rules, your code doesn't compile, period. This leads to something called deterministic performance. Because there's no garbage collector, there are no surprise pauses. Memory is freed exactly when it goes out of scope, not sometime later when the garbage collector decides to run. It's predictable, it's immediate, and it's deterministic. Look at the code example. The function handle request. We create a vector called data. We do some work, we print done, and then the closing braces of the function, and that's where data gets freed. No later, right there. The comment says no GC waiting period, immediate. The final point on this slide is what makes all of these relevant for us as blockchain developers. WASM and on-chain ready, because Rust has minimal binary size and zero runtime overhead. It compiles beautifully to WebAssembly, the formats used by most smart contract platforms. It is generally ideal for resource-constrained environment like smart contracts, where every byte and every microsecond count.